Right, so class. Okay, so for our next topic, we're going to talk about conduction. And so this is the flow of energy from through a material. So I'm going to draw this picture first. Like a nice rectangular object. Alright, so we have this rectangular object, and say the two ends are at different temperatures. Now I'm going to call this TH and this TC for hot and cold. And what's going to happen, because the two ends are at different temperature, we're going to have energy flow in the direction from hot to cold. That's the way, heat flows from hot to cold. Now, normally when we talk about delta, that letter, we always use that to signify a change. Normally, that almost always means like a final value minus an initial value. However, in this one case, we're going to find delta T to be T hot minus T cold. And that way, delta T is always going to be a positive number. And again, we know what direction this heat is flowing. We want to talk about the rate, and so we'll just agree to define delta T this way. And that way we're dealing with positive numbers, and we just know things are going from hot to cold. So we don't have to worry about the direction that things are going. Now, I want to know about the rate that energy is going to flow from one end of this bar to the other. And so the rate, what kind of factors are going to affect things? Since we're talking about a rate of energy flow, that would be power. Power is like energy over time. And I'm going to make a couple observations and say that the rate of energy flow is going to be proportional to the temperature change. So if you double the temperature change between the two ends, you get energy flowing twice as fast. Reasonable assumption. I'm also going to say that the power is proportional to the area. And what I mean by area is this cross-section area. So, like say this is a rectangle. You're looking at it. It's not a very big rectangle. Actually, a very thin box. But say this was like a rectangle in this direction. So you're looking at, so like heat's flowing towards you. So like this cross-section area, that's perpendicular to the direction that the heat is flowing. So yeah, we have to make sure we know which area we're talking about, because another area that we could be talking about would be like the surface area of this object. But no, we're talking about this cross-section area. And I'm going to say that the power, the rate that energy flows, is proportional to the area. And I'm going to say that's kind of obvious. Now, the reason why is, let's say, again, we look at this cross-section area. Say, like in a certain time interval, a certain amount of heat is going to come from this area. If we had a second bar right next to it with the same temperature difference between the ends, we'd have, the same amount of heat flowing. Now, if we just have two identical bars with equal temperature difference, same amount of heat would flow through each region. So basically, if you double the area, you get twice as much heat in a given time interval. So I think that's pretty obvious. Proportional, the rate is proportional to the area. And it's also inversely proportional to the length. So the length of this bar, we're talking about the length in the direction that heat is flowing. So if it's longer, you think about like why energy is flowing from one end to the other. And we have to look at things on a molecular level. So again, this is a solid. And typically for solids, we have every atom is kind of fixed in place. But they can vibrate around that fixed location. So what I mean by fixed in place, even though they're moving, like if you look at one particular molecule and then come back 10 minutes later, that molecule is still going to be there. It's going to be oscillating still, but it's not going to have moved. Now, it turns out in conductors, it's not quite so simple, because in conductors, electrons are free to move around through this object much more freely than atoms are. At least some of the electrons can flow very easily through the metal, and that's why metals are very good at a different type of conduction, electrical conduction. Things like copper wire we use for currents. We'll talk more about that later. But yeah, metals behave a little differently. The atoms are fixed in place, but electrons are free to move around. But anyways, so how does heat get from one end to the other? And remember, the molecules all oscillate, and the more energy they have, the greater, like the more energetic these oscillations are. So if we look at this solid, just as, say, a bunch of layers, like one atom or molecule thick. So like you apply heat to this end here, it's going to, these molecules are going to oscillate more rapidly, and they're going to collide with the next layer of molecules and transfer some of that extra energy to them. And then these molecules are going to collide with the next layer, and that's why conduction happens. It's these collisions, and again, it doesn't instantly happen. If you have like a metal object, which is a good conductor, say you stick that in the fire, you're not instantly going to get burned. It's going to take time for that heat to reach you. And so like the longer it is, the lower the rate of energy transfer. And so, again, I think these are kind of reasonable things. Ultimately, this works. You can always do things experimentally. And, one more factor that affects the rate that energy is going to flow through this material is the material itself. And we can put all this together into a single equation. I'm just going to write down the equation. So I'm going to leave all of this. And then just write so again, we can see here power is proportional to area, it's proportional to the change in temperature, and it's inversely proportional to the length. And this K, this is the coefficient that's a measure of how quickly this heat's going to flow. This depends on the material. It's called the thermal conductivity. And I'm going to write down a few examples. Again, there's a table in the book. Let's solve for K. Just to, say we want the units. So if we solve this for K, we have P L over A delta T. Okay, so P, this would be watts times meter over meter squared times Celsius degree. So the units we get for K, this thermal conductivity, is watts per meter Celsius degree. So I'll just give you a few examples. I'm going to look at and then K in watts per meter Celsius degree. All right, so let's look at aluminum. That'd be 240. Iron, 79. So again, a couple metals. Let's see. So yeah, a few metals. Let's look at some gases. Air is 0.256. So again, if you're next to a fire, for instance, the fire you will get some heat by conduction through the air, but not at a very high rate. However, you also get energy, you also get heat from radiation, which we'll talk about later. Okay, so that's air. Let's look at some other materials. Asbestos. This is 0.09. This is, compare that to other solids like metals. So yeah, this is an extremely low thermal conductivity. Another example, goose down. Again, they use this to make jackets. Again, very low value. Of course, we don't use asbestos anymore because it's toxic. It's very harmful. Water, 0.60. Yeah, so the big difference between some of these solids or wood, I'll do another one. Now, if you look at like wood or asbestos, compare that to iron or aluminum, very, very different values. So things like metals are very good conductors of heat. And these are good insulators, like asbestos. It's a good insulator, but it's, we don't use that anymore because it's toxic. Goose down, again, a very good insulator. And you can use that to make a jacket to keep you warm because, heat's not going to conduct through it very quickly at all. Okay, so this is the basic idea behind thermal conductivity. And I want to do an example here. So I'm going to clear the board. We'll write down what we need. I think I'll write down that equation over here. Alright, so power Ka delta T over L. Okay, so this is an interesting problem. And say we have a house. And inside the house, it's 25 degrees Celsius. And outside, it is 4 degrees Celsius. So, winter class, this is a fairly realistic example of what we're seeing now. And let's look at this wall of the house. So, again, heat's going to flow from hot to cold. So heat is going to flow out of the house into the cold. That's why we need a heater inside the house to replace that energy that's being lost from going from inside to outside. So we want to know the rate that heat is escaping this house. And pretty straightforward problem. Now let's look at this equation. Okay, we need to know what the wall is. The wall is plywood. So, let's see. So for plywood, we have 0.08 watts per meter Celsius degree. That's a thermal conductivity. And now let's look at the equation. We also need to know the area and the length. We have delta T. That's 21 Celsius degrees. But again, just to be clear, we look at the direction heat is flowing, and the length would be the thickness of the wall, and this cross-section area, that would just be the dimensions of the wall, like length and width. Well, using length in two different senses here, but like the X and Y, and then this one is what's passing through it. And so we're given the area of this wall. This is the perpendicular area, which is 35 meters squared. And the thickness, it's a very thin wall, it's 19 millimeters. So again, right now we're just looking at a straightforward calculation, but let's do this. Let's find the rate that energy is leaving. Actually, that's not quite what I want to do. Let's find out how much heat is going to escape the house in 1 hour. And again, obviously it can escape through other walls in the house. We're just looking at how much heat is escaping through this particular wall. So again, here we have power. That's Q over T. Power is energy over time. So basically we find the power and just multiply by an hour. So let's do this. Again, this is a straightforward calculation kind of thing. So, I'm going to write this part up here. Okay. So I might need a lot of room in this direction. So again, Q, this is just power, we'll multiply by an hour. So we have K, which is 0.08. Now, I do things a little differently. 0.08, I don't like decimals if I can avoid them. So yeah, I'm going to write that as 8 over 100. That's 0.08. Now the area is 35 meters squared. And we're dividing by 19 millimeters. And I'm going to get rid of these millimeters. So there's 1,000 millimeters in 1 meter. So those will cancel out. So we have meters squared and a meter, they cancel out. So we have Ka over L, and then times 21 Celsius degrees. So they're going to cancel out. And then we have to multiply by 1 hour, which, well, an hour is 60 minutes, each minute is 60 seconds. So just to save a little space, I'll write that here for now. 1 hour is 3,600 seconds. So let's just write that down. Okay, and finally, a watt is a joule per a second. So a joule per second. So we can say a watt times a second equals a joule. So again, these seconds cancel out, watts cancels out. And again, everything cancels out. We just have our answer in joules. So here we have 8 times 35, 21, 3,600, and then this factor, which I neglected. On the bottom, we just have 19 times 100, which is 10 squared. That would be in joules. Okay, now, since I have it in the notes, I'm just going to look at this. We get, here's our answer, Q equals, I'm going to write it just as it is in the notes, 110 times 10 to the 5th power joules. So again, you just multiply all this out. That's what we'll get. Okay. Now, again, what's the result of this heat flowing out of the room? The room's going to cool off. And we don't want that because we want it to be room temperature. So we'd have to have a heater inside the house warming it up, which costs money. And so we don't want all this heat to escape. So how are we going to keep this from escaping? We're going to put, I'm going to call this L1, or LP for plywood. What we're going to do is let's add a layer of insulation here. Let's call that Li. So here we have Li, that's the length of this layer, like the thickness of the insulation. We don't have the same cross-section area of the wall because it completely covers it. But this insulation is going to have a thickness of 76 millimeters. And the thermal conductivity of the insulation is 0.03, watts per meter Celsius degree. So now this heat, in order to escape to the outside, it has to go through this insulation and the wall. And so again, we're going to say like in 1 hour, how much heat's going to escape? Now, hopefully it's going to be less, but let's check. Now we have a bit of a complication here, because we have this equation, Ka delta T over L, but what do we plug in here? Because we're going through 2 layers. So I'm going to draw this. I'll just draw it and then erase it. So what we have, if we just zoom in on this part, we have our insulation here. And our wall. And this, over here we have 25 degrees Celsius. Here we have 4 degrees Celsius. Now, the observation we want to make, heat is flowing through here. And we can look at this, look at it this way. We're looking at the rate that heat is flowing. And we can look at, say, heat is flowing through the insulation and it's flowing through the wall. But the point is the rate that heat flows through these 2 materials has to be the same. They have to flow through at the same rate. If that wasn't true, like say it's flowing like faster through the insulation than the wall, what would happen is we'd have heat building up at the boundary. So the boundary would warm up. And if we warm up this boundary, that would make the temperature difference between like the 2 ends of the insulation smaller. So like we have a temperature at the boundary. We don't know what that is right now. But let's say that was 10 degrees. Let's just say that's what it was. Again, if heat was flowing through the insulation faster than it's flowing through the wall, that would mean there'd be a net heat building up on this boundary, which would heat it up. And so if we raise this temperature, that's lowering the delta T here and increasing it here. If we change this from, say, 10 to 15, this delta T gets smaller, this delta T gets bigger, and so then that would lower the temperature of the boundary. That would lower the rate that it was going through the insulation and raise the rate that it's going through the wall. And so it's going to reach the state where the power is going through the 2 layers at the same rate. And so our goal is, our approach to solving this problem is we're going to find the temperature at the boundary. So let's say this is P1 and this is P2. So P1 is the rate that heat is flowing through the insulation. P2 is the rate that heat is flowing through the wall. And we're going to state that those are equal to each other. So actually I'm gonna keep this picture up. So I'm gonna just erase it and move it over here. I'll draw the same thing. That's P1 and that's P2. And what we're saying is that P1 is equal to P2. And we're going to use this to solve for the temperature, we'll call it TB. Temperature at the boundary. So again, let's look at our equation. P1, that would be K1, or K, let's just call this KP for plywood. Alright, so we have Kp times this area A times delta T. Now remember, delta T, we agreed that that's always the hotter value minus the colder value. So we'd have 25 minus the boundary temperature. That's delta T. And then divided by L for the insulation. Sorry, this should be layer 1 is the insulation. So I said plywood earlier, but this K, we're talking about, we defined layer 1 to be insulation. So this would be K insulation times A. Oh, sorry. Oh no, that was right. I was getting these kind of mixed up, which layers we're actually talking about. Okay. So again, just layer 1, delta T is 25 minus TB, and layer 1 is insulation. Okay. And now P2, this would be K, now we're talking about the wall, so that'd be plywood times area. Now delta T, that's going to be, the boundary temperature is going to be between 4 and 25. So it's going to be more than 4. Well, see, like if we look at the temperature just going down, it starts at 25 and then it's going to decrease and decrease. Eventually it'll be 4 at the far end. So whatever this is in this boundary, we still don't know that. And then this would be L for the wall. Now, right away, we can cancel out the area. They share that common area. So our goal is just to find this boundary temperature. So I'm going to cross multiply. Let's say Ki LP times delta T. This would be Kp Li times TB minus 4 degrees Celsius. And now we want to distribute this. So we want to get these terms with this unknown temperature on the same side. So we have to distribute. It's going to be a little messy. So that's the left side, and then we have Kp Li TB minus Kp Li times 4 Celsius degrees. And so we want to get these terms, everything is known except for these terms with the TB. So we want to collect those on one side. So again, we'll move this term over to the other side, but I'm going to write it over here. So we have Kp Li times TB. I guess I don't need parentheses there. Plus KILP TB. So again, I moved this term over here, so we're going to move this term to the other side. So here we'll have KILP times 25 plus KPLI times 4 Celsius degrees. And so we can factor our unknown TB. So what we'll have is KPLI plus KILP. So we'll divide by that. I'm going to write this part down. We can't really simplify anything here. It's kind of this messy thing. So KILP times 25 Celsius degrees plus KPLI. And then we're going to divide where we factored out the KPLI plus KILP. So a bit of algebra here to find this boundary temperature. Now, I wonder if I should... Let's look at units for a moment. So I am actually going to write this out. I'm going to clear up some space here. I'll erase everything except our final answer. And then I'll rewrite that. So again, assuming I did the algebra right, temperature at the boundary Okay, so just copy that up here. Okay, so we've got this Ki and Lp for everything, like on both the top and bottom. So again, when it comes to units, you look at the Ki and Kp, they're both in watts per meter Celsius degree, and the lengths are both in millimeters. So we can just ignore those units. They're going to cancel out. We're just going to be left with our temperature. That's the only unit that's going to be left. So we'll get our temperature in degrees Celsius. So we can just plug in the numbers here. So Ki, that would be 0.03. Lp is 19. And then times 25. And then for K for the plywood, that was 0.08 times the length of the plywood, which is 76. And again, that would be, we're going to end up with a temperature in Celsius. And then we divide by KPLI. So that would be 0.08 times 76 plus 0.03 times 19. So just plugging in the numbers. And again, as long as all the K's and L's are in the same units, they're going to cancel out, so we don't have to worry about those. Now, I'm not going to actually do this calculation. It's not hard, but you just, one thing you always want to pay attention to is order of operations. Just make sure you get that part right. But if you plug it in, you find this boundary temperature. I'll write that here. That's around 5.8 degrees Celsius. So if you just plug all this in, you get around 5.8. Okay. Now the question was, now how much heat is going to flow through this wall in 1 hour? And so now that we know this boundary temperature, we can calculate either P1 or P2. You can pick one. Maybe it'd be good to do both, but they're going to be equal to each other. So if you do everything right, they'll just be equal to each other. But let's just calculate, say, P1. So that'd be the insulation. So we have Ki times A times delta T, which would now be 19.2 Celsius degrees. So we know what delta T is now. Going from 25 to 20, that would just bring us down to 20. we want to go an additional 0.8, so it'll be 19.2. So that's Ka delta T over L, which would be 76 millimeters. So again, that's what we get by plugging in P1. As a check, you could also plug in, let's do P2 as well. So here we'd have K for the plywood, that same area. Now delta T in this case would be 1.8 Celsius degrees. Difference between 4 and 5.8. And then we divide by K for plywood. So again, if you plug in the numbers and check P1 and P2, you should get the same number. And then Q would be, let's just say P1 times T. P1 times an hour. And if we plug in all the numbers, what we would get is 9.5 times 10 to the 5th power joules. And that's why this number was not written in scientific notation, because I knew we were going to calculate like the amount of heat lost with insulation, and that was going to be 9.5 times 10 to the 5th. It's just a lot easier to compare these numbers if they have the same exponent. So like this, we're comparing 9.5 and 110. This number is obviously a lot smaller. And so putting this layer of insulation, that really increases efficiency. Heat will not escape your house nearly as quickly, and less energy use. So it's cheaper, and obviously better for the environment. So yeah, that's why insulation is used. It saves you a lot of money, and we use less energy that way. So okay. Yeah, that's basically conduction. And those are the kind of problems we're going to consider, just heat flowing in a particular direction. It could be a lot more complicated, but nothing that we're going to do. So, you could consider a general case where, say you have some weirdly shaped metal object, and you apply heat at one area, and like, what's the temperature going to be at some other point on this object? That could be a fairly complicated thing. We're just going to look at heat that's flowing in one direction, just like one end or the other. So remember, it's either straightforward, just plugging into an equation, or if it's different materials, or if it's even just the same material, but for some reason you want to know the temperature at some point in the middle, then you have to do this. You have to draw that boundary layer and say that the rate of energy flow is going to be the same on both sides of that boundary. And then allow you to calculate the temperature like anywhere inside this material. So even if you just had, say, like a solid metal bar, you could find the temperature at any point in between. See how it varies from one end of the bar to the other. In this case, we had two different materials, so we kind of had to do it this way. But yeah, that's the idea behind conduction. And that'll be it for this one. And next we'll talk about radiation.